What is up? I am back in this grind. I'm sorry I haven't been doing much because I have school stuff to do. This is multivariable calculus, and we are going to start in the 3.4 tangent planes and approximations. So we have already established our formula for the tangent planes last time in 3.3. However, this is a review right here. F of x, y is approximately equal to f of x naught, y naught plus f of x, or not f of x, f sub x times x minus x naught plus f sub y times y minus y naught. Also, you could also rewrite this as z equals z naught plus f sub x, x minus x naught, plus f sub y, y minus y naught. That works as well, right? They work, right? They all work. These two formulas work. However, this formula only works when z is equal to f of x, y, as in the z-axis, or the x and y plane, the point in the xy plane, is determines the height of that the graph is going to give, right? So that's the only point where z, you can replace the f of x, y with z, which usually you can, because graphically it just makes sense for a point in the xy plane to represent a height elevation in z. However, we will see later on that might be a little bit tougher to handle when you have more than one variable, or more than two variables. So let's do some approximation exercises. Approximate 1.9 negative 3.1 if f of xy equals 3xy squared. Now, this is a little bit dumb because this is a polynomial, and what we are actually having in this formula is polynomials, right? So these are just polynomials. Whatever we're trying to, yeah, we're going to do quadratic approximations next, and this is a polynomial. So it's kind of it's a little bit dumb to approximate f of x, y equals a polynomial if what we're going to be making is polynomials. However, just for practice, we'll do this. It's very easy, so we will do it. Okay, ready? So what is this number close to is what we have to figure out first. So that's step one. What is this number close to? And I'm going to use the text feature. What is this number, the number close to, the number inside, or I guess you should say the x, y inside of f of xy. So what is the xy close to? What is x close to? What's 1.9 close to? It's close to the number 2, right? So f of 2. And then what is negative 3.1 close to? Negative 3.1 is close to negative 3. So first we want to find this, right? So number 2 is find the approximations of x and y. And usually you'll have whole numbers like this, and it's very easy to approximate. For example, 3 times 2 times negative 3 squared is simply 54. Right, so that is the very easy approximation that you can get from this. However, that's not what we want, right? This is f of 2, negative 3. It's not a good approximation of f of 1.9, negative 3.1. It's close, and if it's continuous, it should be good, but it's not a very good approximation yet. And we will find a better approximation if we do step 3, which is find the tangent plane approximation of this vector, of the, no, not of this vector, of this graph. So we got to find this tangent plane approximation of f equals 2 comma negative 3. We have to find f sub x first. F sub x is equal to 3y squared, and f sub y is equal to 6xy. Right? So what's step 4? Step 4 is we have to find f sub x at that particular point, which is 2, negative 3. And f sub y at that particular point, 2, negative 3. So what's f sub x at 2, negative 3? It's 27. And what's f sub y at 2, negative 3? It's negative 36, right? So those are big numbers. Now 5, write the equation down. I'm gonna say z is equal to f of x, y. And then I'm gonna say z is equal to z naught 54 plus 27 times x minus x naught. What is our x that we're trying to find? So in this formula, the x naught is actually the first number right here, 1.9. The x naught is what difference we want, or no, I'm sorry. The x is the number that we're trying to find, and the x naught is the number that we can easily find. So it would be 1.9 is the number that we're trying to find, x, minus x naught is minus 2. So 1.9 minus 2, and then plus, or minus, I should say, 36 times negative 3.1, or yeah, negative 3.1. Okay, I need to move all of this to the left. So negative 3.1, I don't know if you guys can still see it, minus negative 3. Which gets you what? Which gets you 54 plus 27 times, or yeah, I guess I should say z of 1.9 negative 3.1. So 54 negative 27 times negative 0.1, and then minus 36 times negative 0.1, which will get you what? This will get you 54.9, and that is the final answer. That's your approximation of f of 1.9 negative 3.1 right there. Next question, a little bit harder because tan is not a number that we like to mess with. So let's take my work and then we will make it smaller. Okay, this is really messy. But take my work and then we'll make it smaller, and then we will pull this up and approximate g of negative 2, negative 0.2, negative 0.2. What is negative 0.2 and negative 0.2 closest to? So I'm just going to say it right now. They're both close to 0. So it's x equals 0, y equals 0. Now let's find f or g of 0, 0. So g of 0, 0 is what? Is e to the 0 times tan of 0 times 0. So what's 0? What's 0 times anything? It's 0, so e to the 0 is 1. So g of 0, 0 is 1. Now number 3, let's find f sub x, or g sub x. G sub x is equal to, well, chain rule. So let's do e to the x tan xy, right? And then we have product rule. So multiply that by the derivative of the inside, tan of xy plus x times, and then the derivative of that, which is secant squared of xy multiplied by the derivative of the inside times y. So that's a pretty messy formula. So because it's pretty messy, we probably want to find g sub, that's why we want to find g sub x at that value first, right? We don't want to find g sub, we don't want to find the entire formula and then put it into that equation, because that would actually make it more messy. Like if we had x, y's, tans, secants, e's in f sub x and f sub y, and we write something like z equals z0 plus tan of xy x minus x0, something like that, that's just going to be really messy. It's not going to be fun. So okay, so what we do is now we find g sub y. So g sub y is actually a little bit easier because the top won't be as disgusting. G sub y is e to the x tan of xy multiplied by the derivative of the inside, which is x, right? It's just x times tan of xy, or x times the derivative of tan of xy, which is this time it's squared because we're taking the derivative with respect to y. So it'll actually be secant squared of xy times x, but I just put a square on top of it. So it serves the same purpose, and that is what you get. And if you evaluate this, what you get is a very nice conclusion, because since x and y is both 0, we have that 0, right? This becomes 0, so x squared is 0, so g sub y at 0, 0 is 0. And then for g sub x, tan of 0 is 0, and 0 times this chunk is 0. So it's 0 plus 0, which is 0. Anything times 0 is 0. So g sub x at 0, 0 is also 0. So by approximating this, what we get is z is equal to z0, 1, right? Plus 0 times x minus x0 plus 0 times y minus y0. I'm not even going to write the numbers down because we know this is just going to be 0 and 0, and we can approximate g of negative 0.2, negative 0.2 is 1. And that is our answer. Right? It's not a very nice answer. In fact, the approximation is probably pretty far off, but this is a linear approximation. It's not the best type of approximation, so that's what we're going to get. A better type of approximation, though, is a quadratic approximation, which I've kind of leaned into a little bit. Approximation of quadratic form will have a square on them. Now, I don't know if you guys recall, the Taylor series in single variable calculus is this. This is a Taylor series, and this is the linear approximation part of it, which is exactly y minus y0 equals right, f prime of x times x minus x0. This is a linear approximation in single variable calculus, and this is exactly the same thing, except I replace the f of x with y, right? So this is the linear part of it. This, however, is the quadratic approximation, right? Which is f of x0 plus f prime of x0 times x minus x0 divided by 1 factorial plus 1/2. This looks nice in my eyes, but you can just divide this by 2 factorial, and this would look the exact same if you erase the 2 like this. So it's 1/2 times f double prime of x0 times x minus x0 squared plus dot 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 plus f sub n, or the nth derivative of f at x0 times x minus x0 to the n over n factorial. That's the Taylor series, and this is the quadratic approximation in single variable calculus. However, in multivariable calculus, the quadratic approximation for 2 variables is like this. f of x0 plus y0, right? This is the linear part of it, so I'm just gonna highlight the linear part of it, right, which is what we had right here. And then this is the quadratic part of it, which is the entire thing. This is the quadratic part. So it's the linear plus the quadratic part to get you the entire quadratic approximation. 1/2 times f sub xx, the second derivative of f with respect to x, twice, times x minus x0 all squared plus f sub yy, same thing, squared, plus, there's no 1/2 for this one, it's just 1 f sub xy times x minus x0 times y minus y0. And why is there no 1/2? Because we forgot f sub yx. But f sub yx is exactly the same as f sub xy if the function is continuous and differentiable. So because the function is continuous, we assume that the function is continuous differentiable at that point. We don't need to worry about differentiability, right? So what does this give us? What does it give us? This gives us a quadric surface. This gives us a quadric surface that is tangent to the point. That sounds a little bit weird, right? It gives us a quadric surface. Usually it either gives us a like an elliptic paraboloid, a like it probably won't give you a cone. It will give you an elliptic paraboloid, a hyperbolic paraboloid, or a I think an ellipsoid. I think, but I'm not sure about that. Don't quote me on that. I think the elliptic paraboloid is probably the best thing that you could get out of this surface, out of this type of surface, but you will get a quadric surface for this thing to approximate the function. And obviously quadric surfaces go kind of nuts, so it's not a very good idea to approximate using a quadric surface if it goes too far away, right? This actually, it probably won't give you an ellipsoid just because it has to be a function of x, y. So it'll probably give you an elliptic paraboloid or hyperbolic paraboloid or maybe a half cone, right? I'm not sure. Probably not a half cone, actually. So elliptic or hyperbolic paraboloid. There you go. Those are your two options that you might get. Maybe some combination of the two, or maybe something else completely different, but it's not the other quadric surfaces that don't pass the function test. So using a quadratic approximation, approximate the value of this given if g of x, y is this. So first, let's find values that are close to 1.01 and 0.99. That's very easy. X equal 1. Actually, I'm going to switch this. This becomes positive 0.99 because negative 0.99 doesn't exist. X equals 1, y equals 1. Right? Simple. 2. Let's find g of 1, 1. Natural log of 1 is 0, so g of 1, 1 is 0. 3. Let's find g sub x and g sub y. So what's g sub x? G sub x is a natural case of the chain rule. It's 1 over xy times y, which is 1 over x. And by association, g sub y is 1 over y as well. So it's 1 over xy times x times the derivative of xy, which is with respect to y, which is x. So it's 1 over y. Number 4, let's find g sub xx. What's g sub xx? G sub xx is the derivative of 1 over x with respect to x, which is negative 1 over x squared. What's g sub yy? Negative 1 over y squared. What's g sub xy? What is the derivative of 1 over x with respect to y? Or 1 over y with respect to x? It's 0. It's a constant. So, what does our quadratic approximation become? It becomes, actually, before we do that, let's evaluate. So what's g sub x at the particular point? So I'm just going to put, this is very abusive notation. This is not actually the correct notation, but I'm just going to put a big line across every single function that I'm trying to evaluate, and they're all evaluated at 1, 1. So this is 1, this is 1, this is negative 1, this is negative 1, and this is 0, right? Pretty standard so far. So that's step 5. Step 5. Step 6 is let's start forming the function. So g of 1.01, 0.99 is equal to g of 1, 1, or not equal, approximately equal to 0 plus 1 times, so first we're doing 1 times x minus x 0. So our x is the x that we're trying to find, 1.01. So in fact, it will probably be more useful to say x0 equals 1 and y0 equals 1 at the beginning, minus 1, right? And then plus 1 times 0.99 minus 1. Yeah, so this is f sub x, this is f sub y. Now we go on to crunch time with the squared components. So it will become f sub xx, or I guess 1/2 times f sub xx or g sub xx, I'm sorry, which is negative 1 over x squared, is negative 1 times x minus x0 squared. What's x minus x0? It's this, 1.01 minus 1 all squared, plus 1/2 times negative 1 again, times 0.99 minus 1 all squared. Right, this is f sub yy multiplied by, or g sub yy multiplied by 1/2 multiplied by this. And then plus 0. Because 0 times anything is 0, I'm not going to try to do the differences. So what do you end up getting? You end up getting 1, or this is 0.01. This is minus 0.01. This is what? This is minus 1/2 times 0.01 squared, minus again 1/2 times negative 0.01 squared. So this cancels out. Now we get what? We get negative 1/2 times 0.01 squared plus, because we factor out the negative, and 1/2 negative 0.01 squared, which ends up being exactly 1 in 20,000. Because this is 0.0001, so 10 to the negative 4th power. Actually, no, sorry, 1 in 10,000. This is 0.0, or yeah, so this is 0.0001, because these add up, and then you get 0.0002 divided by 2 is 0.001, and I forgot to add a negative. It's negative this. It's not 6.1. I'm sorry. This is bad writing for me. There you go. So it's 10 to the negative 4th is the answer. Now with functions that have more than one variable, this is what the linear approximation looks like. Not quadratic, linear, right? So I'm assuming we have an n tuple, which is a coordinate with n points, x, y, z, t, whatever, all the way to omega, right? Where omega represents an arbitrary stopping point. What you'll get is that's equal to f of x0, y0, z0, etc., all the way to omega 0, plus f sub x times x minus x0, f sub y times y minus y0, f sub z times 0 minus 0, 0, etc., etc., until you get to the arbitrary constant f sub omega times omega minus omega 0. So how do we do this? We do this exactly the same way that we've been doing it, just with more variables now. So what do we end up getting? We end up getting h, or we have to first declare that these are your variables that you're going to use for the linear approximation, and they're all going to be 0 because these numbers are really close to 0, right? 0.1, negative 0.1. 2 is, let's find h of 0 4 times 0, 0, 0, 0, which is e to the 0, which is 1. 3, let's find h sub x, h sub y, h sub z, and h sub t. So the thing about these is this, right? This is just a chain rule when you take the derivative. But I don't want to write e to the x squared plus y squared plus z squared plus t squared all the time. So I'm just going to say this is h, right? So what you end up getting is h sub x is equal to h multiplied by 2x, because the chain rule will give you the derivative with respect to x of the inside, which is 2x, and then 2y, 2z, and 2t, respectively. So now we got to find all of this, step 4, all of this at 0, 0, 0, 0, not 0, not, you thought I was going to stop at the second 0, no. all of it at 0, 0, 0, 0. And anything multiplied by 0 is 0, so they are all 0. Right? It's kind of boring. A boring resolution, because what you're gonna get is 5 is equal to everything is 0, right? So basically we have 0 times x minus x0 plus 0 times y minus y0 plus 0 plus 0, so everything is 0. So we say that h sub 0, 0, or h of 0, 0, 0, 0 is equal to, or no, not equal to, approximately equal, I'm sorry, 0.1, negative 0.1, negative 0.1, and 0.1 is approximately equal to h of 0, 0, 0, 0, which is 0, or 1, I'm sorry, 1. So that is the correct answer in this case. Now, this is what the approximation value can also be rewritten as, right? So this actually looks a little bit more clean than what we have right here. So this is what we can do is we can, or I'm sorry, right back here, move this to the left, and then what we get is f minus f0, right? I'm just going to say this is f0 because it's x0 and y0. So f, or z minus z0, you can also say that. So f of xy minus f of x0 y0. So that's how you get delta f, change in f. And then f sub x, change in x, plus f sub y, change in y. And I'll just add this for my OCD. So, yeah, so partial derivative times the change, plus partial derivative times the change. So, as we take the limits approaching 0, so as delta f approaches 0, basically, limit as delta t approaches 0 of delta f over delta t. I'm pretty sure you've seen this in single variable before. I don't know if you see it in the board, but limit as delta t approaches 0 of delta f delta t is equal to df dt, right? But in this case, we don't have delta t approaches 0, so what we just say is limit as, or what is the limit as delta f approaches 0 of delta f? We get df. This is very, very abusive. The answer would actually be 0, but df is such a small change in f that it might as well be 0, right? So this is called the total differential of the equation. So if you take a total derivative of an equation, you're going to get something like this. And we'll touch on more of this later. We'll touch on more on this later. This is not the partial derivative. This is the total differential. Total, you're taking the derivative of it totally, not the partial anymore. So this is how you take the derivative of a function totally in multivariable calculus. And you get a weird form. df is equal to f sub x dx plus f sub y dy. So we don't actually know what any of this means until we have x as a function of something else and y as a function of something else, right? So if we said x is equal to x of t, then we could say df dt is equal to df dx times dx dt plus df dy times dy dt, or del f del x times dx dt plus del f del y times dy dt, which is what is called the chain rule, the complex chain rule, which is what we'll do next time. But for this time, you just need to admire these equations, and we will find the total differential of this function, and then we will approximate it, because we can use this to change to this, right? This can be changed to this pretty easily. So step 1, what we want to find is the total differential. So let's do the question in order. We could just go through the entire thing, but let's do the question in order. So df is equal to f sub x. What's f sub x? So that's actually step 1. F sub x is equal to 1 over 1 plus, or I mean, I'll leave the top blank, 1 plus x squared y squared. Right, that's the derivative of arctan. And then the top would be the derivative of the inside, which is 2xy. What's f sub y? F sub y is equal to same thing, the derivative. So 1 plus x squared y all squared multiplied by the inside, so x squared, or multiply by the derivative of the inside, x squared. Right, so our total differential is df is equal to 2xy over 1 plus x to the fourth y squared dx plus x squared over 1 plus x to the fourth y squared dy. That's our total differential. Very easy. Not very hard at all, right? So this is the linear approximation, basically. So how you could change this is you could say that delta f, or f minus f0, which is what I'm going to put right now, f minus f0 is equal to this, which I don't want to I don't want to copy it, so I'm just going to put quotation marks, y minus y0. Right? So that's your you already found the partial derivatives. That's half the job. That other half of the job is trying to find two numbers that are close. So which numbers are close to 11 and 9? So here's the thing about this equation that's really, really dumb, right? Arctan doesn't have a nice number for 10 and 10. Arctan does not have a nice number for 10 and 10. We don't need to use 10 and 10 though, because this thing doesn't say approximate using 10 f of 10 comma 10. This thing says approximate using f of 11 comma 9. So if we want a true approximation, a real approximation, even though it's wildly off, it's not a very good approximation, it's an approximation nonetheless. Arctan does not give you a good number for 10, for x equals 10, y equals 10. Arctan of 1000 is something that I don't know. However, what I do know is arctan of 1. So because I do know arctan of 1, I'm going to set x equals 1 and y equals 1. So what we're going to end up getting, this is actually what I did not think of when I was making this question, is f of 10 and 10 is not very good. So this is kind of like freestyle. So x equals 1 and y equals 1 will give you, the next step is f of 1 comma 1, which is arctan of 1, pi over 4. Right? This is a lot better. So tan of pi over 4 is 1. So arctan of 1 is pi over 4. Right? What's arctan of 1000? I don't know what arctan of 1000 is. That's really hard to, calculate. So I just simply take the arctan of 1, and that is what you'll get. You will not get a very good approximation, but you will get a approximation that is a number and not a bunch of functions. We already have our f sub x and f sub y, so what do? We just need to evaluate, and that's it. So what we get is 5f minus pi over 4 is equal to, or let's say f of 11 comma 9 minus pi over 4 is approximately equal to this evaluated at 1, which is 2 times 1 times 1 over 1 plus 1, so that's 2 over 2 times change in x, which is, what is the change in x? Is 11, which is what we want to find, minus 1, plus, what's the change in y? 9 minus 1. And if we put 1 in here, we'll have 1/2. So what will we get? We'll get f of 11 over 9, or no, I'm sorry, f of 11 comma 9 is approximately equal to pi over 4 plus 10 plus 4, which is 14 plus pi over 4. So that's ugly. That's not very nice. However, that's what we're going to have to deal with if we want a number answer. If we don't want a number of an answer that's a number, we could do 10, 10, and then we'll get 200 over like a million plus 100 over a million, which are probably like a lot better of approximations than using 1, 1, but we won't get a number. So this is an approximation. It's not a good approximation. I wouldn't even say it's a good approximation. It's just an approximation, right? It's a, like, It's like when someone tries to throw a dartboard blindfolded. Someone tries to hit a bullseye in the dartboard blindfolded. They're not gonna get it, but they made an effort because, yeah, given the conditions that they were in, they made an effort. So that's why I made an effort to try to do this. So this is what I get, right? Anyways, I'll see you next time for complex chain rule.